we should be able to show you the phase plan and trajectories, but I couldn't find it. But somehow I'm going to manage it. Don't worry about it. Okay. So yesterday, what we did, we were talking about the solution of a system of first order homogeneous linear differential equation. Of course, I was assuming that this is all the differential equations in this system. They are with constant coefficients. Okay. And we saw that they can be reduced to the single matrix form, this, okay? And again, we saw that the solution of this system depends upon the eigenvalues of the matrix A, which is given by the characteristic equation, this one, okay? Fine. So yesterday, we started with when the roots of the characteristic equations were real, right? And at the very beginning, we were talking about distinct roots, of course, distinct real roots. And in that case, we didn't have any problem at all because we know that with distinct eigenvalues, you can find out, what? You can find out what? Distinct eigenvalues.
Linearly independent eigenvectors.
Yeah, you can find out again eigenvectors which are going to be linearly independent, right? So we are always going to find a fundamental set over there. So we didn't face any problem at all. Okay, and then we went ahead to repeated roots. We went ahead with repeated roots. Okay, and of course, still now I'm in real, like when the roots of the characteristic equation, they are real. When they are complex, I will move to that later on. Okay. So if we have repeated root and then we consider, two cases. So what happened? Like that means you are going to have some roots λ1 of say multiplicity m. So then again this gives rise to two cases. So what may happen? The corresponding to this λ1, I am going to find, or I may be able to find, m linearly independent eigenvector. Okay, so that will be the first case, and in the second case, it may so happen that corresponding to this root. Characteristic root λ1, that is the eigenvalue λ1, I may be able to find only one eigenvector. Okay, so this is kind of a troublesome case. Okay, so today what I am going to do, I am going to show you both the cases through suitable examples and how to tackle this situation when you are left only with one eigenvector. So whether it allows to find me the remaining m-1 eigenvectors, which is going to constitute a linearly independent set. Okay, so that's what we are going to do. So for that, let us take one example first. Just give me a sec. Okay, so let us take this example. 1 minus 2 minus 2 minus 2 1 minus 2 2 minus 2 1. Already, probably you can see that there is some kind of pattern here. Okay. Okay, so what we are doing there, we are trying to solve a system of differential equations, of course, with constant coefficients. It is given by this one. Okay, so here now, if I want to find out a minus lambda I. So that is going to be 1 minus lambda minus 2 minus 2 1 minus lambda minus 2 minus 2 1 minus lambda. Okay, so this is equal to 0. So what are you going to do? You are going to do directly, or you would like to reduce it somehow? Okay, so I would like to reduce it somehow. Okay, because I have minus 2 here, right? If I add row 2 to row 3, so then definitely I'll be getting rid of this element. That may be, let us see what happens here. I'll try to do it quick. 1 minus lambda. So this is 0. This is minus 1 minus lambda. This is again minus 1 minus lambda. Are you getting my point? Here what I have done, R3 is simply R3 plus R2. Is it okay with everybody? Fine. So this leaves me, hopefully I have written all the, okay, fine. So this is going to give me, this is, I am with this one. So then this is going to give me your lambda square minus 1. And see, there will be a minus sign here. There will be a minus sign here. Minus minus plus into this again. This is minus. So this is minus 2 lambda. Okay. And then this is going to become plus 2. And then this into this. So that is going to give you 2 plus 2 lambda. Again, there will be minus sign here. So this is going to be 2 plus 2 lambda. So this is equal to 0. Okay. So then, because I would like the matrix to be here, so that I don't lose it. I'll be needing that. Okay. So this implies lambda minus 1. So this is going to be lambda square minus 2 lambda minus 3. I think I am going to get this as lambda minus 1. Sorry, lambda minus 3 into lambda plus 1, right? Okay. And from that, you will see that it is simply 8 into lambda plus 1. Is it okay with everybody? Fine. Okay. So if lambda plus 1 comes out here, so then I have lambda minus 1, lambda minus 3. So this is lambda squared minus 4 lambda plus 3. Am I done? Minus sign. Am I okay?
Sir, this will be minus 3.
Minus
3. Lambda square minus 4 lambda minus 3.
Just a minute. No, because I am taking lambda plus 1 out. So lambda minus 1 into lambda minus 3. Huh? Because then I'm going to be left with only 8. I think I have done some mistake somewhere. Just let me check. Minus. Is it okay? Just a minute. So this is minus lambda into minus lambda. This is lambda squared. Then plus minus 1 minus 1. Okay. Then minus. So that makes it plus into this. So this is fine. 2 minus 2 lambda. This should also be fine. Plus 2.
Sir, I think that will be 1 minus lambda.
Which one?
That lambda minus 1 will be 1 minus lambda.
This is 1 minus lambda. Yes. So basically, yeah. So basically, this is 1 minus lambda. Sorry. Yes. Thank you. So it is going to be minus lambda squared. Okay. So it is going to be minus 3. So it is plus 3 minus 1. It is going to be plus 2 lambda, right? Lambda squared plus 2 lambda minus 3 plus 6, I guess. I think I should be okay. Fine. So this is going to give me lambda plus 1, and then this is what? Lambda squared minus 2 lambda. So minus 3 plus 8, that was plus 5. So this is going to be minus 5.
That will be 4 lambda plus 3 lambda plus lambda.
Just a minute. Minus 3
Yes, sir.
that is minus lambda into minus 3. That is 4 lambda, sorry. That is 4 lambda. I was looking at something. See, minus lambda into minus 3, that is 3 lambda. Then lambda into 1, only lambda. So, yeah, plus 4 lambda. So, if it was plus 4 lambda, this is minus 4 lambda, and this is minus 5, right? This is minus 5, this is equal to 0. So, eventually, this is going to give you lambda minus 5, lambda plus 1, right? Yeah, okay, I'm fine. So basically, I am going to get eventually lambda plus 1 whole square, lambda minus 5, this is equal to 0. Okay? So you have 2 repeated roots, one repeated root, sorry. This is equal to minus 1, and lambda 3 is equal to 5. Okay? So basically, my aim was to reach here. Aim was to reach this. This one is very important. Okay? Fine. So I'm going to erase this. So now, okay, fine. See, now let us try to find out. Let us try to find out what is the eigenvector or eigenvectors corresponding to the value of lambda 1 equal to lambda 2 equal to minus 1. Okay. So now your a minus 1 I. So this is simply plus 1 you have to add to the diagonal element. So 2 minus 2, 2, minus 2, 2, minus 2, 2, minus 2, 2. Is it okay with everybody? Yes?
Yes, sir.
Right? So this is going to give me, say, 1 minus 1, 1. Then again, this is the same as this one. So this is going to go, and this is nothing but what? This is nothing but, negative of this one, right? Is it okay with everybody?
Yes, sir.
Yes, sir.
Right?
Yes.
So basically, second row and third row are going to vary after a series of row transformations, right? Is it okay with everybody? Fine?
Yes, sir.
Right? So you simply see by now, in fact, I am trying to find an eigenvector. It is like k1, k2, k3, right? So now you have this. Now you have this. So if you look at this, so basically I have k1 minus k2 plus k3 equal to 0, right? So I have many choices here now. See, this negative one is beautifully set. Negative one is beautifully set. So firstly, what you can do, you can take k1 equal to 1, k2 equal to 1, k3 equal to 0. Is it okay? Fine?
Yes, sir.
Right? And secondly, what you can do, you can say k1 equal to 0, k2 equal to 1, k3 equal to 1. Is it okay?
Yes, sir.
Fine? And please remember, they are not the only choice. You can have some other choices also. Don't worry about it. I could have chosen these to be equal to 0, these to be equal to 1, this to be equal to -1 also. That would also have given me an eigenvector. Okay. So what we have found out, that I can have eigenvector k1 bar. This is what I say 1 1 0, right? And then k2 bar. This is 0 1 1, right? 0 1 1 as my two eigenvectors corresponding to the same eigenvalue -1. That was my point. Is it okay with everybody? Fine. And if you look
Yes,
at
sir.
k1 and k2, k1 bar and k2 bar, you will say that they are linearly independent, isn't it? Because obviously one is not the scalar multiple of the other. Is it okay? Fine. So I have found out k1 and k2, and now I need to find k3. Okay, and I think k3 you will be able to find out, right? You are silent.
Yes, sir.
Okay, maybe let me do it completely. So I have found out. So now let me try to get, maybe it will be some kind of practice. So now corresponding to lambda 3 equal to 5, I am trying to prove it. So then these three are going to change. These three are going to change. So this is simply going to be -4, -4, -4, isn't it? Is it okay?
Yes, sir.
Fine. So do we have something in common? Okay, anyway, let me, sorry. So this one, so no, I have nothing in common, but anyway. So what I am going to do, I'm going to lift it above. Okay. So 1 -1 -2, and then this below. Let me make it 2. 2 1 -1, and again let me make it 1. These are all negative, right? 1 2 1. Okay. So now it will be easier for me to walk out. So this is going to be 1 -1 2 0 0. So basically this minus this, so this is going to be 3. This is also going to be 3. Okay. So this minus 2 into this, so this becomes 0. -2 into -1, 2. 1 plus 2, this is 3. Again, -2 into 2 into -2, that is 4. 4 -1, this is 3. Is it okay? Fine. Simply here, what I have done, R2 is R2 minus R1, R3 is R3 minus 2R1. That is what I have done. Is it okay? Fine.
Yes, sir.
Right. So eventually I can make these two as 1 1, and this is 0 0. Right? Okay. So can you give me a choice for my third vector, K3? Yes.
1 1 0. No, sir.
1 1 0. Yeah, that is fine. That is fine. Is it going to give me 1 1 0? Will it be?
No, sir.
Why not? I need these to be 1 minus 1, right? Isn't it? Why not make these two as 1 minus 1 and these are 0? Will it work? Will it work? Okay, let me make it easier for you. Let me add these two.
So
This
1
one.
minus 9.
So this is going to be 3, right? This is going to be 3, right? 103. Yeah.
Yes.
3 1 minus. Yes.
3 1
1 minus 1.
Minus.
minus 1. Yeah. Okay. Yeah. Good. So K3 is this. Okay. So your a general solution is going to be x equal to C1. Then this is 110 e to the power minus t plus C2 011 e to the power minus t plus C3 3 1 minus 1 e to the power 5t, right? E to the power 5. Okay, so even now, see, like say this particular example, this particular problem of solving the differential equation, it was kind of straightforward, isn't it? It was kind of straightforward. Like we were lucky that corresponding to an eigenvalue of multiplicity 2, we were able to find exactly 2 eigenvectors, right? Which were linearly independent. Okay. Now let me take another case where you will see that it may not be possible to do so. Okay. And then we'll try to find out what we are going to do. Okay, fine. Okay, at least I have a 0 entry in the third row. I'm like, that should reduce my load. Okay, so now if I want to find out a minus lambda equal to 0, so that is going to give me what? 5 minus lambda. Okay, you think about 5 minus lambda. This is minus lambda. This is again 5 minus lambda. Okay, so that is going to give me lambda squared minus 5 lambda minus 4. Okay, right? And then minus then plus 4 minus anything you can use. Let me use plus 4. So then this is simply 5 minus lambda. I'm good. It is even better for me. Is it okay with everybody? Right? So this is going to give me 5 minus lambda. Then yeah, lambda square minus 5 lambda, right? Because it is going to be lambda square minus 5 lambda minus 4 plus 4. Is it okay? Fine. So basically, I am going to get from here lambda minus 5 whole square into lambda. This is equal to 0. Is it okay? Fine. Yes.
Yes,
So
sir.
what I have got lambda 1 equal to lambda 2 equal to say 5. Okay, and maybe it is up to you. Lambda 3 equal to 0. Okay, fine. This is that information is good enough, right? Okay. So now let me start with lambda 3 equal to 0. Let us do the easier thing first, and after that I will move to the difficult part. Okay. So then I mean a minus lambda I. That means a minus 0I itself is nothing but this one, right? So basically I have a minus 0I, that is your 5 minus 4 0 1 0 2 and 0 2 5. So what I would like to do, I would like to do 5 minus 4 0 0 2 5. Okay, so then 1 0 2. Let me make it 0 0 here itself. So basically I'm multiplying it by 5 and subtracting it from here. So this is minus 4 and this is 1 2 into 5. So this is minus 10, right? So now you see here this is 2 5, isn't it? 2 5 and this is the multiple of 2 5. Is it okay with everybody? The second row is a multiple of 2 5. Is it okay?
Yes, sir.
Fine. So that is why I am simply going to write this as 2 5 0 0. Is it okay? Fine. So now you give me a solution. K3. So K3 will be equal to
minus 4 minus 5 2
minus 4 minus 5
2.
2. Yeah. Okay. Minus 4 minus 5 2, right? And again, remember, this is not unique. Huh? You can have infinite number of choices. Okay, fine. So now let us come to the interesting part. I mean, now if I do this is a minus 5y, so this is going to be, these two are going to be 0 0. This is going to be minus 5, isn't it? This is going to be minus 5. Okay, so again as before, yeah, I think it is perfectly safe, right? 2 0 minus 4 0. Is it okay? Right? So that is why I can simply, eventually I can transform it into this, then 0 1 0 0 0 0. Is it okay with everybody? Because I am skipping many of the transformation, raw transformation. Is it? Are you comfortable with that? Are you comfortable with what I have done?
Yes, sir.
Okay.
Yes, sir.
Fine. So now obviously this is going to leave me with, because this is 1 0. Obviously my second component that has to be 0, right? Isn't it?
Yes, sir.
And about the first and third, I don't have any choice. I can have 2 minus 1. Is it okay?
Yes, sir.
2 minus 1. Fine? Okay. So now, I mean, beyond this one, say let me call it say k bar. So except for this vector or its scalar multiple, this system, I mean, doesn't give me any other eigenvector corresponding to the eigenvalue 5. Is it okay with everybody? Just tell me whether you have been able to appreciate the difference between the earlier problem and this particular problem. See, earlier problem also it had repeated roots, but fortunately, corresponding to an eigenvector of multiplicity 2, we were able to find exactly two linearly independent eigenvectors, right? But here I am left only with one, right? Now I think you can appreciate the difference. What is the difference between those two situations? Although both the situations led me to, repeated roots, fine? So now let me call this say K1. Let me call this K1. K1 equal to 0 minus 1. That is good enough for me. So let me keep that information intact. So now let me again move to theory. Okay. So now I'll stop here, and now I'm going to tell you how to find out the remaining eigenvectors corresponding to an eigenvalue of multiplicity m. So that means how to find out the remaining m minus 1 eigenvectors corresponding to this. Okay, the same eigenvalue. So for that, what you have to do? Okay, fine. So maybe might be a linearly independent set of eigenvectors for an say eigenvalue of multiplicity m. Okay, so this is what we are going to do. And again, this situation is when you can find when you can find only one eigenvalue corresponding to that you can find only one eigenvector corresponding to the eigenvalue of multiplicity m. Okay, fine. So suppose I have just a minute. Should I write it eigenvectors? Just a minute. We shouldn't write it as eigenvectors. Let me remove this now. Let me call it set of solutions. Set of solutions. Because eventually, just let me tell you, eventually what was happening in earlier case. So I was finding K1 and K2, right? And eventually I had x1, that is K1 e to the power say lambda 1t, and x2 that was equal to K2 e to the power again lambda 1t, right? But if you look at the vectors x1 and x2, they were linearly independent, right? So that is what our aim was. Okay. So what we are trying to do here, we are trying to find out a linearly independent set of solutions from that one eigenvector corresponding to an eigenvalue of multiplicity m. So then, like x1, the very first one, you can say suppose that eigenvalue was lambda 1. So definitely once I find out the single eigenvector corresponding to lambda 1, I can always write out my first solution vector as that. Is it okay? Fine. So what we are going to do, the second solution vector, because this is a repeated root, it is, I am going to write it as okay. eigenvalue, say lambda 1 of 100. Okay, so then your x3, this is x1. Okay. Yes. What should I write here?
M minus 1.
Okay, fine. Any question? Any question?
So key mean what?
K, yes.
Oh. So we can find out some eigenvector k1 once, but what are the others?
Yeah.
Key mean.
Okay. I think I got what you wanted to ask, although it was not very clear. See, here I have written down certain formula for you, right? I have written down certain formula for you. Only thing that is obvious from the formula, or the only thing that is, I mean, readily available in our hand is simply this one, isn't it? Agree or disagree? Because
Yes, sir.
right, I have been able to find, like say, one eigenvector corresponding to that eigenvalue of multiplicity m. Right? Beyond that, I don't have anything, isn't it? Beyond that, I don't have anything. So what is going to happen? It is going to boil down to find out. It is going to boil down to find out all the remaining your eigenvectors. So basically what you are going to do, say once you have this, I can easily find out this one. Okay, where here for k to 1, I am simply going to use some multiple of k1 1. Okay, so you are going to see how it works. Okay, I'm just going to show it to you. Okay, fine. Okay. Let me just give you one example. Then I'll come back to that. Okay. So let us suppose that I have been say for the time being, what we are going to do, we are going to do it for an eigenvalue of multiplicity 2. Okay, eigenvalue of multiplicity 2. And whatever I am going to derive, that thing you will be able to easily extend it to an eigenvalue of multiplicity m, which is greater than 2. You don't need to worry about it. So, say suppose lambda 1 has multiplicity 2. Okay? And suppose corresponding to this lambda 1, I have already found out an eigenvector k bar. Okay? So that means x1, I can easily write it as k to the power lambda 1 t. Is it okay? K bar to the power lambda 1 t. Okay? So now let us assume that your x2 equal to k t e to the power lambda 1 t, right? And plus some p e to the power lambda 1. So basically this k is nothing but this k 21. Okay, so k21 simply I have written it as k11. Okay, and then this p is nothing but k22. Is it okay with everybody? In the previous formulas that I have written. Okay, fine. So now you know that your x2 is a solution of the system of first order linear equations given by that. Okay, so now if I plug this x2 here, so then what is going to happen? Maybe let me write down this first so that it is easier for me to visualize later on. So this is simply say okay. So then if I try to find out this derivative, so this is simply your k lambda t, sorry, lambda 1 t e to the power lambda 1 t plus k e to the power lambda 1 t, and then plus p lambda 1 e to the power lambda 1. Okay, fine. So now let us make some adjustment. Okay, so this I can write as, now look at your this one and this one. Okay, so I can write this to as a minus lambda 1 I k t is the power lambda 1 t, right? And this one I can write it as, from this and these I can write it as a minus lambda 1 I this p, and then minus k to the power lambda 1. Is it okay with everybody? Is it okay? Fine. And this is equal to 0 bar or 0?
Bar, 0 bar.
0 bar. Okay, fine. And again, like say, since that e to the power lambda 1 t, this is always non-vanishing, from here I can write this. Okay, fine. And again, since t is arbitrary, what I can do, so this is going to imply what? This is going to imply your a minus lambda I k, this is equal to 0, right? And this is going to imply me A minus lambda 1 I, then P, this is equal to K. Is it okay? Fine. Is it okay? Fine. So from here, so what you will do? This is going to give you the vector K bar, right? So once you have found out K bar, you simply plug in K bar here on the right hand side, okay? And then solve this system of equations. That is going to give you the vector P. Is it okay?
Yes.
Yes. You will see the proof. I mean, like I'm still holding on to that, and from there again I'm going to move forward. Okay. Now, see, this is only for an eigenvalue of multiplicity 2. So can you tell me? Can you give me a way how to go about an eigenvalue of multiplicity n? Then? Can you visualize a procedure for that? Can you visualize a procedure for that? Eigenvalue of multiplicity more than 2?
So,
Yes.
So if k m minus 1th vector I get k m minus 1, then k m and m we get by the equation a minus lambda 1 I to the power m minus 1 k m minus 1 equals to k.
So you are saying to the power n minus 1.
Yes, a matrix.
You are thinking about exponent of matrix.
Oh, not that is not true. Okay.
See,
Just
I'll
a minus
say,
lambda 1. Yes, sir, just.
see, basically, see, once you have found out k, say suppose I have like say an eigenvector of multiplicity m. Okay, say I have already found out the very first one, right? So then it is going to be like say p1 and then p2 up to pm minus 1, isn't it? If I am able to find out all those remaining m minus 1, that along with this k, that is going to form a linearly independent set of vectors. Is it okay? Fine. Like say they are linear combination. Is it okay? So then basically what I am going to do. So this is going to be P1. So in your next, you are going to get something like P2 equal to this P1. So eventually what you are going to get, you are going to get something like this. Is it okay with everybody? Right? So this is definitely possible. Okay, so we'll be getting something like this. We'll be getting something like this, and that is going to give you a way of finding out the remaining solutions or remaining eigenvectors. Okay, fine. So now let me move to this. Let me come back to this one now. So that means what we are going to do. So I have to simply something like I am trying to find out, say, suppose I am trying to find out the vector k2. So I have to simply do this. Is it okay with everybody?
Yes, sir.
Yes.
Right? So
Yes, sir.
now let me write down the augmented matrix. Okay, let me write down the augmented matrix. So a minus lambda I, when lambda equal to 5, from there it is going to give me 0, minus 4, 0, then 1, minus 5, 2, and 0, 2, 0. Okay, and k1 it is 2, 0, minus 1. Right? So as before, I'd like to raise this up 1 minus 5 2 0. Then again see these are again multiple of each other. Is it okay everybody? 2 0 minus 1, fine. Is it okay?
Yes, sir.
The first and third row. The first row is simply minus 2 is the third row, right? So what I'm going to do, simply I'm going to write it as 2 0 minus 1. That's it. So 0 0 0 0. Is it okay with everybody? Fine. Okay. So that means the second entry, if I call it small k2, I am getting as minus half. Okay, so now the rest is simple. So if I plug in k2 equal to minus half, this is going to give me 5 by 2. Isn't it? Either you make this 0 or this 0 and make the adjustment. So if I make this 0 and if I make it minus 5 by 2, I am done. Are you getting my point? Yes? Are you getting my point?
Yes, sir.
So I can write the just this as minus 5 by 2 minus half 0, or I can simply write it as 5 1 0. Is it okay? Say 5 1 0. It is going to work. Just a minute. 5 1 0 is going to just a minute. 5 by 2 into no sorry just give me a sec. You shouldn't try to do what I am trying to do. Okay, you can you take that as because these are not 0, remember, these are not 0. Can I still make adjustment? Is it going to satisfy that? I think it is not going to satisfy that, right? Are you getting my point?
Yes, sir.
Right? Generally, I mean, I would have gone for something like that. But see, if I simply multiply it by minus 2, it's at 5 1 0. But 5 1 0 is not a solution of this, right?
Yes, sir.
Yes, sir.
Right? That is fine. But just a minute. But still, I think it will be okay. Even if I take 5 1 0, even then it is going to be okay, because I am seeking only a vector here. Whether I take that vector or its scalar multiple, it is not going to make change to the to the final general solution, isn't it? Although, see, I now from solving this system of equation, I have got k2 equal to this, right? Eventually, in my solution, what is going to happen? In my solution, what is going to happen? Your x2, x2, it is going to be something like your k1t e to the power 5t plus k2 e to the power 5t, right? k2 e to the power 5t. Are you getting my point? Okay. Just a minute. Whether you can take. No, you cannot take. You have to take this. You have to take this, because what is going to happen in C1x2, right? Sorry, C2x2 in the linear combination, C1x1 plus C2x2. So then C2 will come here only. C2 doesn't come here. Are you getting the point? Right? So that is why you have to stick to this. You have to stick to this. Okay. Although, like say in our brain, we may think that some scalar multiple is going to work. No, not in this case. Okay, fine. So now in the final solution, what you simply write your this one. X2 is going to be something like this. X1 you already have. X1 you already have in terms of K1, and then you have X3 also, and from there you get a linear combination. Yeah, somebody wanted to ask me something. Yes.
Sir, the solution for this equation will be minus 5 by 2 minus 1 by 2 0 plus minus 2 minus 1 by 2 0 into small k3.
Minus. Can you repeat it? I'm not getting it.
Yes, ma'am. Yes, sir. Sorry. This you have written k2 bar is equal to minus 5 by 2 minus 1 by 2 0 only. So the solutions of this system will be this k2 plus scalar multiple of minus 2 minus half and 0.
Minus 2 minus
Half 0.
no why no why you are bringing a scalar multiple? That I'm not getting. What? Just a minute.
From the first,
no.
from the
what
first
I'm
equation,
saying-
from the
Yes.
first equation,
Which first equation? You are talking about, say,
sir,
this
we
one?
have found that no, sir. So we have found k2 is minus 5 by 2, right?
Yeah.
Oh, sorry, minus 2.
K2 is
Minus 1 by 2, small k2.
okay, fine. Yeah, okay.
And then from R1, row 1, or K1, small k1 is dependent on k3.
Yes.
So by that, we will get the solution is in the form of this vector.
Okay. So rather than making K1 as 0, you are trying to make K3 as 0.
Yes, sir. But instead of k3 0, we can take another scalar also. So we will get different solutions.
No. See, here the problem is it has to satisfy this system of equation. The right hand side is not 0. That is why we don't have liberty with this scalar multiple. That is my point. Okay. Now see, let me tell you. Like say, this is fine. If I multiply it by minus 2, it is fine with me, right? I can write it as 5, 1, 0. But in that case, you have to multiply K1 also with minus 2. That K1 also with minus 2 you have to do. Only with that adjustment, it is going to work. Okay, fine. Okay, I think, like say, you can again ponder over it at home. What I have told you, even if it is not clear to you, right? Why you cannot take the liberty of taking any scalar multiple of this? This is because this right hand side is not 0 here. That's it. Okay. So now, so maybe one thing I can do, like, okay, maybe here itself I can do, say, phase plan. I'll come to complex root later on, and phase portrait. Okay, say, okay, Can somebody tell me what is a phase plane or phase space? Yes. Okay, I'm. Let us assume that I have something like this. Okay, so where A is a 2 by 2 matrix. Huh? A is a 2 by 2 matrix. A is a 2 by 2 matrix. Okay. See, let me tell you. So generally, what we do, we are interested in the evolution of some variable while solving a differential equation. Okay. So in that case, here the independent variable t, if I consider it as time, say, if I consider it as time, okay. So then, suppose I am solving a system of two first order ODE, right? Through this framework. So then, say suppose you had like say the dependent variable as x1 and x2. It can be x1, x2, x3 also. Okay. So then what we can do? Say suppose this is my t. Suppose this is my x1 or x2. Say this is my x1 or x2. Okay. So basically, what is happening? By this vector, this is simply x1, x2. Okay. So now, suppose my let's say suppose okay. Say suppose this violet graph is x1 and the blue graph is x2. Okay, fine. So basically, this is simply this one is simply what the graphs of x1 and x2 with respect to t. So far, so good, right? It is clear to you. So now, what is phase plane? What is phase plane? So these solution curves, if instead of plotting t versus x1 and x2, if I plot it like say x1 versus x2, right? Although both x1 and x2 are functions of t, but hiding t also, we can track how x1 and x2 are evolving. Okay, so for that, say initially, say at t equal to 0, what was happening? Your x1, say suppose this is say 3, say suppose this is -2, right? So then in x1 x2 plan, what is going to happen? Initially, I'll have to take the point 3 minus 2. So basically, say suppose 1, 2, 3. I'll start from here. Is it okay with everybody? Right? And then suppose like this is 1, this is 2. Huh? And suppose this one is like say this one is like say maybe 2.2, and this one is minus 1.5, say something like that. Okay. So then what is going to happen? Then next point, obviously next point I am going to take this one and this one, this one and this one, and so on. So in that way, what we can do, I can get a curve here in x1, x2 plan. Is it okay with everybody?
Yes, sir.
Yes. So then I mean that curve is going to be called, that curve in x1 and x2, it is going to be called a trajectory, right? So basically, it is showing. Say suppose here if I consider x1 and x2 to be the coordinates of a particle at time t, right? So then it is going to show me what? The path of the particle over time, isn't it? So basically here, whatever curve I am going to take, that is going to give me the pathway particle at what? Throughout a certain time range. Say here, if I take time from say 0 to 10 here, right? So here, this curve is going to show me that the particle started at time t equal to 0 and it is ending at somewhere at time t equal to 10. Okay, so in order to make it more clear, so what I'm going to do, I'm going to show you two curves here. See, this is time evolution. This is time evolution of two variables. Okay, so you assume that the like say the black one, it is with respect to the variable v3, and the green one, it is with respect to the variable v5. With respect to this v1, and v1 is nothing but time. Is it okay with everybody? This graph is fine with you, right? Okay. So now in this particular figure, you can see that it is kind of periodic, isn't it? It is kind of periodic. If you look at these two curves, you can see that they are kind of periodic. It is repeating after some time, isn't it? See here, you can see it is like a sine wave. Again, it is repeating here. Is it okay with everybody?
Yes, sir.
Fine. So now, if I plot V1 versus V5, let us see what happens. So what I'm going to do, this is the software package I'm using. So I'm going to just hide one, and then here instead of, so see here, now only V5 is there. So if I click it here, both V3 and V5 is available here. So now I'm just removing this. So now instead of V1, let me replace it with V3. Okay, so that is going to give me the trajectory like the way I have drawn in the blackboard. So if I do that, here you cannot see anything, but now you can see that I'm getting this. See, I'm getting this graph. Are you getting the point? So this is nothing but the trajectory of the particle, and you can see that this is a closed one because the evolution of those two variables, I mean V3 and V5, they will periodic. So that is why they will be, I mean, what their trajectory is, it is going to follow a closed curve. Is it okay? Are you getting my point?
Yes, sir.
Yes.
Yes, sir.
Right. So here, see here that variable v1 is absent. So maybe I exactly don't know. So maybe say it is starting somewhere here at a particular time, and then I mean it is moving around and it is going back like this. So what I can do, I can show you. I can show you the just a minute. Just no, sorry. What I can do? Yeah. So this was. See, this is the data file. So here you can see that this one, like say this column, the first column was for time. So it is going from 391 to 400, something like 400. Okay. So for that time range 10, I'm plotting those two curves initially. So this was V3, this column 3 is V3, and this is V5. Okay, right? So whatever you see here, like say, whatever you see here, initially it is this. Is it okay? Fine. So now if I change it to, if I send it to V3 and V5, then you can see that it has become a closed curve. It has become a closed curve. Is it okay now? Is it clear how we are getting the trajectory? Yes?
Yes, sir. Sir,
So, yeah.
sir, when we are drawing V3 versus V5, then V1 is behaving like a parameter.
Can you repeat it? When I am
When we are
V3
drawing
versus V5. Yes?
V3 versus V5, then V1 is behaving like a parameter.
Yeah, exactly. V1, yeah. V1 is a parameter common to both, I mean, V3 and V5. Yes. Basically, V3 and V5, they are functions of that parameter V1. That's it. So, yeah, what you were saying is correct. This is nothing but whatever we finally got, V3 versus V5, that was simply a parametric curve. So, you can, in other words, you can see that, you can say that I have eliminated T from the equations of your V3 and V5. For that matter, here, say if I get a curve like this here. So basically, just by eliminating T from the functions x1 and x2, I am getting a curve like this. Okay. So these plan where I am plotting all the trajectories, it is called phase plan. Okay. So if I am considering a function of 3 variables, say suppose I am considering the trajectory of a particle in 3-dimensional space, so then this is going to be called a phase space. Okay. Now, what is phase portrait? Now, interestingly, what we did here, we were tracking both the variables x1 and x2. If you look at that, with respect to a certain initial conditions, right? So here, what we did, x1 and x2, here my initial condition was something like x0, y0. It was something like 3 minus 2, isn't it? Or x10, x20, it was 3 minus 2. Is it okay with everybody? Right? So that is why it started with something like 3 minus 2 here, and I was tracking. Okay. So similarly, with different initial conditions, I am going to have different trajectories. Is it okay with everybody? Fine. Okay. So if you take all the trajectories together in this x1, x2 plan here, or in the phase plan, so that portrait that you get of all the trajectories, it is called a phase portrait. That's it. Is as easy as that. Okay. So in my next class, I will come back to roots of the characteristic equation, or root of the characteristic equation being, I mean, complex roots. And then what I'm going to do, I'm going to give you an idea of how the trajectories are going to look like. Okay, so if you have complex roots, and then once I'm done with that, I'm going to move to autonomous system. So over there, I'm going to talk about stability, and I'm going to emphasize more on visualizing the eigenvector corresponding to different eigenvalues arising out of a system of linear first order equations. Okay, so then it will be more clear to you what we are trying to figure out here, what we mean by stability when a solution is said to be stable, right? So in order for that, before that, we'll be needing to study critical points. Okay, so okay then, I'm going to meet you next Tuesday then. So can you tell me, I mean, Thursday, what time does your classes start? Thursday. Today, say. Today, somebody has an earlier class also? Yes?
Yes, sir.
No, nobody has a class